Hello students, we are continuing with chapter 4 and we're going to be doing some math in this. And what I want you to pay attention to is just how we're just generally getting to moles and using the equation to use mole ratio to go between reactants and products. So let's get started. The first section is solution stoichiometry, and then I'll specifically talk about titration. So here's an example of a precipitation reaction. Reacting lead nitrate, aqueous, with ammonium iodide, also aqueous. So these are representations, something really similar. Here I have K+, but envision that's ammonium. And these ions are just floating around in solution. That's what aqueous means, dissolved in water. And if they can dissolve, the ionic compounds can dissolve, you'll get the ions floating around in solution. So the cation of one can encounter the anion of another and find each other and form a precipitate. This may or may not happen. It depends on the solubility rules. So in this case, lead combined with iodide does give a solid. Here we have lead iodide, that's yellow in the beaker below. And what you also get out are the spectator ions, still floating around aqueous in solution, the ammonium ion and nitrate. So we write it all intact, but at the end, what you have is lead iodide. You see this alternating array of cation and anion. Notice that's what makes that solid. You should be able to draw something like that. And then the spectator ions are still floating around in solution, the ammonium and the nitrate. Okay, so the type of problem you'll encounter is something like this. What volume of a certain concentration of the ammonium iodide is required to react with a certain volume and concentration of the lead nitrate? So we have to work with volume and molarity because we're dealing with solutions. But if you multiply liters times molarity, you get moles. And when you're in moles, that's how you can relate reactants and products, or reactants and reactants. So let's solve this problem. I just rewrote the problem. And when you encounter something like this, look at what you're given. You're given a certain amount of one of the reactants, the volume and molarity. So right there, you have the amount, the number of moles. All you do is put the volume in liters, so 0.75 liters multiplied by the molarity, 0.22. Make sure the volume and molarity are the same guy, lead nitrate. Don't swap the molarity of some other guy. So multiplying these two, liters cancel, you get moles. So that lets you now be in moles of lead nitrate. But I asked you about ammonium iodide, the volume of ammonium iodide. The only way you could get volume is knowing moles first, moles and using molarity. So the only way you can get information about ammonium iodide is the equation. And you'd use the big coefficient 1 to 2. So for every 1 mole of lead nitrate, you react with 2 moles of ammonium iodide. So that's mole ratio from the equation. The moles of lead nitrate cancel, and you now are in moles of ammonium iodide. And the final question was, what is the volume? I have the moles. So then now I can use molarity, expand the units of the molarity to moles per liter. So you have 0.66 moles, put that in the denominator to cancel moles, per 1 liter. And it'll always be per 1 liter for molarity, and put that in the numerator. Crunch your numbers and you should get 0.50. Okay, let's do something else. We're going to do something called a titration. This is a common lab experiment to do to determine the concentration of a solution. So what you do is you do an acid-base reaction, and you know acids and bases can neutralize each other to give a neutral solution, producing water. So you're going to use a known concentration of base and add it to an acid of unknown molarity. You can even swap these. Use a known concentration of acid, add it to a base of unknown molarity. then you're going to react those, and you need to find out when you've reached this point of neutralization. So you have to add some sort of indicator, some sort of dye, such as phenolphthalein, where phenolphthalein is colorless when it's acidic, but it turns pink when the solution is basic. So then you know the transition from acid to base, to an acidic to a basic solution. So here's an example. We have a burette, and this is a long column, and it's like an inverted graduated cylinder. And here's my base. I'm just showing it as OH minus. And in here in the Erlenmeyer is our acid. I'm showing this as H plus being present, and my dye, my indicator. So before the titration starts, it's colorless. As you start adding base, and we know the concentration of this guy, and we're going to record the volume that we add, you're going to react with all the acid in here. You'll start seeing it turn pink. You'll swirl the flask and see that flash of pink disappear. But when you reach a point where it's just a permanent faint pink, just one little drop goes from clear to permanent faint pink, that's where you reach the end point. And that is basically one drop right after all of the OH minus and H plus are completely reacted, meaning all of your acid is neutralized. So that's very, very close to this, what's called the equivalence point, that point of neutralization. So we record the volume that we see here, and we use the known molarity at this equivalence point. Okay, let me just show you how this is done on paper. Here's a titration problem. Let's say I use 2.5 molar sodium hydroxide in my burette, and I'm going to titrate a certain volume of acid. You need to know the original volume because later you want to calculate the concentration of the acid. But the first thing you're going to do is find the moles of acid in there. How? You're going to add the base, record the concentration where you get the permanent faint pink, and then you're going to use that volume added times molarity to find the moles of sodium hydroxide. And from there, you can use the equation. And you're probably asking what equation. You're going to write a balanced equation. So pause here, try to take a stab at this. Write a balanced equation between sulfuric acid, H2SO4, and sodium hydroxide. Make the products. And try to do this reaction, just like we did the solution stoichiometry one. Okay, here's the balanced equation. H2SO4 is an acid that is diprotic. It gives up two H pluses. So if there are two H pluses floating around and a sulfate, I need two hydroxides to react with the two H pluses. So I put a big 2 here, and that gives me two waters because one H plus and another hydroxide, OH minus, gives me one water. So I have 2 and 2 and 2. And then what's left over is Na2SO4. Okay. I already mentioned the question here. So we're doing a titration. And the question is, what's the original concentration if 44 milliliters of sodium hydroxide is required to reach the end point? So the key here is to connect the 44 milliliters of sodium hydroxide with the 2.5 molar sodium hydroxide. There are a lot of numbers here, so just keep the sodium hydroxide numbers together. So you'll multiply those to get the moles of sodium hydroxide. Then, because I'm asking you about acid in the equation, anytime I ask you between two different guys in an equation, you have to use mole ratio, 2 to 1. So then use mole ratio from the equation. For every 2 moles of sodium hydroxide, I need or I react with 1 mole of sulfuric acid. Crunch the numbers, you get the moles of sulfuric acid. And then if I asked you how many moles, you would have given me that answer. But if I asked you what's the original concentration, give me the molarity. And molarity is moles per liter. So use the moles you just calculated. And what liters? Don't use the liters from sodium hydroxide, you use the original liters of sulfuric acid, which is 0.65, and you get 0.85 molar sulfuric acid. The last thing I want to mention is another topic on acids and bases, and there's some very important naming that we do for these sort of acid-base reactions. Just to let you know, you can take an acid and react it with water as a base. And so what that means is the acid gives up H plus and the water picks up H plus. That's another definition of being a base. So then here we have nitric acid. It's going to give up an H plus to the water, and the water becomes the hydronium ion. It picked up an H plus, so it's now H3O plus. And then after the acid gives up an H plus, he's left with nitrate, NO3 minus. So what I want to mention is there are these pairs. Do you see how nitrate is the main guy here? And with the H, he's the acid, but without his H, he can be a base. And we call it the conjugate base here. Conjugate base, because he's a conjugate base of this original acid. So these are conjugate acid-base pairs in red. If you look from the perspective of water, water is acting as a base in this reaction shown, and he picks up an H plus to become H3O plus. H3O plus is a conjugate acid. It's an acid because it now has an H plus he could give up if you went in the reverse direction, for example. So these are also conjugate acid-base pairs. Okay, that ends this segment, and we'll continue next time. Bye.